So what I'd like to do today is show you an example of a system of differential equations that you can actually solve without using methods we're going to learn in chapter 3 called eigenvalues and eigenvectors, using methods from chapter 1 actually. And then I want to tie this to this matrix exponential idea, which for the moment is only something that we can do with a computer essentially, though in general, though we will be able to do it by hand with this example. It's going to be an example of something called a partially decoupled system. The partially decoupled system that I do in lecture 17, I believe it is, corresponds to something called an upper triangular matrix. For variety, in class today, we'll do an example that corresponds to something called a lower triangular matrix. So here's going to be our partially decoupled system. dx dt equals negative 2x. And dy dt equals 3x plus y. Let's make that our partially decoupled system. Why is it called a partially decoupled system? Well, a coupled system would be one where the right-hand sides would, in both equations, depend on both x and y. X and y would be completely coupled together. A completely decoupled system would be one where dx dt's right-hand side only depends on x, and dy dt's right-hand side only depends on y. Okay? Meaning the equations could be thought about and solved independently of each other. They would be completely decoupled. This is partially decoupled. X's differential equation, right-hand side, only depends on x. X is decoupled from y, but y's differential equation in part depends on x. So there's a partial coupling, or you might say a partial decoupling. How could we possibly solve such a system of differential equations? Well, because x is decoupled from y, we can solve for x first. We could separate variables here, or since it's fairly simple, we could just guess, right? We know the solution of this. The general solution is going to be x is an arbitrary constant times e to the negative 2t. That would be the general solution of the x equation. Let me also do something I will do often in coming lectures. Let me add generic initial conditions. X of 0 equals x naught, y of 0 equals y naught. Generic initial conditions. This is going to be a big deal for us. Okay. Yeah, in most homework problems, you have particular numbers here and here, and that's fine. But we also want to be able to think about this stuff with generic initial conditions, arbitrary initial conditions. And if x of 0 equals x naught, well, then that's what c is, right? Because e to the 0 is 1. So I get x naught e to the negative 2t. When I write a c, I'm thinking of c as arbitrary, and this is being a general solution representing infinitely many functions for x. But here, yeah, x naught is arbitrary, but I'm thinking of it as something fixed. So I'm thinking of this as being one particular function, though we will ultimately change our perspective and think of x naught as a variable too. Whether something's a constant or a variable is all in how you're thinking about it. And the thinking about it makes a difference. All right, well, that's great for x, but what about y? How can I possibly solve for y if it's coupled with x like this? Well, now that you've solved for x, let's go ahead and use this form of it. Go ahead and substitute it in right there as a function of t. When I do that, I get dy dt equals 3. I'm replacing x right there with this function of t times x naught e to the negative 2t plus y. And even though this differential equation looks kind of complicated because it's got an x naught in it, x naught's just a constant. This is a differential equation you can solve either by the method of undetermined coefficients or integrating factors. It's a linear differential equation in y. Y is just the first power. No y squareds, no e to the y, no sine of y. It doesn't matter that this is a nonlinear function of t. That doesn't matter. This is still a linear equation that can be solved either with the method of undetermined coefficients or integrating factors. Let's, for variety, use integrating factors. I think maybe we didn't get enough practice with that before. To use integrating factors, I'd want to get the y on the other side, so I'd subtract y from both sides. And then the integrating factor is going to be, call it mu, e to the integral of whatever the coefficient of y is, which in general can be a function of t, but in this case is a constant, -1. In other words, the integrating factor is e to the negative t. Do I need a plus c here? No, because it's good enough just to have one antiderivative for that exponent. The method then, again, takes that integrating factor and multiplies it on both sides of the differential equation. That's why it's called a factor. And it's an integrating factor because it makes the left-hand side easy to integrate, if you look at it in the right way. Don't forget, one common mistake is to forget to multiply it on the right side. I need to do that. And I'll get 3x naught e to the -3t if I do that. And yeah, the magic of integrating factors is that this thing on the left is the derivative with respect to t of a product, the integrating factor times the unknown function y. And yes, as always, it's traditional not to write y of t here, but in your mind, you should realize y is a function of t. This is the product of two functions of t here. And if you double check that this derivative equals this, you'd have to use the product rule. You'll see it works. There's e to the -t, the left function, times dy dt, the derivative of the right function, plus the right function y times negative e to the -t is the derivative of the left function. This is the product rule that will go from here to here, remembering that y is a function of t. And now, since this is a derivative, it's easy to integrate. Now integrate, I won't even bother writing an integral symbol. The left side integrates to the integrating factor times the unknown function y. The right side we integrate with respect to t. If you want to be careful about it, you do a substitution like u equals 3t or -3t. You'll get -x naught e to the -3t. Plus, you do want an integration constant here, c. Right? Double check it by differentiation. You differentiate this. The chain rule gives an extra factor of -3, giving you that. Solve for y now by multiply both sides by e to the positive t, or equivalently divide both sides by e to the -t. And we go back to a -2t. And with the c, we get an e to the positive t. There's a general solution of the dy dt equation. Now let's take our generic but fixed initial condition y naught equals y of 0 and solve for this c. Plug in t equals 0. We get -x naught plus c. C is not going to equal y naught. C is going to equal y naught plus x naught. Or x naught plus y naught if we wanted to go in alphabetical order. All right, so we have solved. This now solves our generic initial value problem. Done copying that, or how are we doing? This now solves, when I combined x and y, our generic initial value problem. I can write the answer in vector form. Capital Y vector of t equals, what is x? X was this. That's nice and simple. X naught e to the -2t. What is y? Y was what we just found down here, there, except now replace c with x naught plus y naught. That's going to be -x naught e to the negative 2t plus the c, again, is x naught plus y naught. That gets multiplied by e to the positive t. There's our solution. I've solved effectively, this is really cool. I've effectively solved infinitely many initial value problems at once. Isn't that cool? I can now plug in any particular numbers for x naught and y naught that I want into there, and I've got my unique solution of that particular initial value problem. I think that's pretty cool. In the lectures, so I'm about to do something the book doesn't do, but I've hinted at this before. In the lectures, I now give this a new name. Well, I write actually y is a variable, and I give this function of t a new name, phi of t, except since it's a vector, I make it a capital phi. Capital phi of t, leave a little space there, and make a subscript vector y naught, where vector y naught is a column vector whose components are little x naught and little y naught. And this equals this thing that we have right here. Why am I doing this? A few different reasons. For one, other textbooks, other differential equations textbooks sometimes do this. So if you had to read another differential equations textbook, you would see this. Emphasizing that technically this is abuse of notation, right? Writing y equals y of t, at least, is abuse of notation, because then you're using y in two different ways as a dependent variable and a function name. Here I'm kind of just using it as a function name, but here I'm using it as a dependent variable. So it's a function, and the function here is, I don't want to call it f. I don't want to call it capital F. I don't want to give it the same name as the vector field because it is different than the vector field. So I need some other letter, and the traditional letter to use is phi, or phi if you prefer. Another important reason that I'm doing this is to connect it to something called a flow, which I don't think I've mentioned in the lectures through lecture 16, but I start mentioning in lecture 17. The flow of a vector field. It's not discussed in the textbook in the way that I discuss it in the lectures. It's something new. It's in the extra readings near the top of the next week on Moodle, that you start learning about the flow of a vector field. Again, as I said at the beginning of class today before I started recording, this is to tie together linear algebra and differential equations in large part, but it's also going to go beyond that and help us understand differential equations more deeply. Okay, it's related to this flow idea. It in and of itself is not a flow, but it's related to it in ways I'm not going to explain right now. For the moment, what I want to do, though, is I want to relate it to this matrix exponential idea that I've already started talking about in the lectures. It turns out that this vector here can be written as a matrix times a vector. What matrix times what vector? Well, if you think about the definition of a matrix times a vector as a linear combination of the columns of the matrix with the components of the vectors as the weights, we can break this vector into pieces. Let's break with x naught in front of one vector and y naught in front of another vector. Don't quite have room here, and I need to go up a little bit here. Let's write this as x naught times e to the negative 2t in the first component and negative e to the negative 2t in the second component. Oops, that's not quite right. Sorry. X naught times, okay, the second component is going to have two things in it because x naught is getting multiplied by negative e to the negative 2t there and positive e to the t there. So I need a negative e to the negative 2t plus e to the t. I'm looking right here and here when I write that. I see x naught is multiplied by both of those factors. And the first component is just multiplied by e to the negative 2t. Plus y naught times a vector. Y naught's vector is simpler. There's no y naught in the first component, so that's a 0. There's a y naught in the second component next to an e to the t. So all I've done here is just rewritten this vector in as a linear combination to emphasize that I could think of it now as a matrix multiplication. A matrix with these columns times a vector with components x naught and y naught. The first column of the matrix is going to be this first vector here, e to the negative 2t and negative e to the negative 2t plus e to the t. The second column in the matrix is going to be this vector, 0 e to the t. That's a negative 2 there. It's a little hard to see. Negative 2t right there. This matrix is a function. It's a function. It's a matrix valued function of t. Isn't it? Right? T is a variable. This is a variable matrix. It's a function. Plug in a value of t, you get a matrix out. If t is some specific number, it's a specific matrix. But t could also be thought of as a variable, so this is a variable matrix. This is the matrix exponential of a matrix A. What matrix A? What is A? I haven't said what A is, actually. A is the matrix for the original linear system. And this vector here, x naught, y naught, is the vector I already called y naught. What is A? Yeah, A is the matrix for this original system. If I wrote that system in vector matrix form, A would be negative 2, 0, 3, 1. That's what A is. Look at those coefficients. That is called a lower triangular matrix. Lower triangular matrix. Why is it called a lower triangular matrix? Because the only non-zero, well, okay, the only numbers that are 0 are the numbers, in this case, only one of them, up and to the right of the lower triangular part, consisting of this part here. That's kind of an awkward way of saying it, but that's basically accurate. The part on the main diagonal and below could have zeros in it, but in this case, it doesn't. The part above and to the right of that is a 0, and if we had a bigger matrix and it was a lower triangular matrix, it would be all zeros above and to the right of it. Such a lower triangular matrix corresponds to a partially decoupled system like this. And you might remember, with upper and lower triangular matrices, determinants are easy to find. For example, they're the numbers on the main diagonal, the product. Right? You learned about that with the section on determinants. If you got an upper triangular or lower triangular matrix, the determinant is the product of the numbers on the main diagonal. They're simpler. If I had all non-zero numbers in here, you get the determinant's a bit more complicated. But this generalizes to bigger matrices too. That's the matrix A that I'm raising. Well, A times T is being raised, made the power of E. You've never done that before in your life, right? You've never raised E to a matrix power before. Well, we're doing it right here. Now, you might scratch your head and say, well, what did we really do here? Is this just a new name for it? At the moment, it feels that way, doesn't it? You can define e to the AT in a more rigorous way than just saying it's the answer that you get out here. I'll tell you how you define it right now. You define it as an infinite series of matrices. Oh, what did I just say? I, the identity matrix, plus A times T plus A times T squared over 2 factorial plus A times T cubed over 3 factorial. Wait, does that look familiar? That should look familiar from calculus 2. That should look like the series for e to the x, except A times T is playing the role of x, and I is, I guess, playing the role of the number 1. Yeah, this is a generalization of the series for e to the x from calculus 2, the Taylor series. And this is the definition of that matrix. But I mean, we're leaving under the rug all sorts of questions you might wonder about, like, what does it mean to add together infinitely many matrices? What does that even mean? That's a big issue, actually. And we're throwing it under the rug. All I'm saying in writing this is you can define this in a rigorous way this way. And it does turn out to equal this for this particular matrix A that we have. Let's just confirm that with Mathematica. Matrix form gives you output that looks like a matrix. That's why I'm including matrix form here. Matrix exp computes the matrix exponential of T times some matrix A. I'm putting the T in the left as I more traditionally will. The matrix A again was -2, 0, 3, 1. Hopefully the output of this looks the same as the matrix that we just got, except it's not expanded. No. Okay. Not quite sure why it's not expanding it there. Simplify. Okay, I guess that did it. Compare these two matrices, they are the same. Okay. So at the moment, we're relying on technology mostly to compute the matrix exponential quickly, at least. Yes, I did it because I solved the system and told you how to think about it as a linear combination and therefore as a matrix times a vector. But we don't know yet how to deal with matrices that are more complicated, like that don't have any zeros in them. That's for chapter 3, eigenvalues and eigenvectors. But it's also a job for change of coordinates. All the stuff at the very beginning of the semester about change of coordinates, including skewed coordinates, is going to come back in a big way with the purpose of helping us compute this matrix exponential. Is one purpose. If you feel like you don't completely understand this, it's okay. That happens to practically everybody. You got to just keep working at it. Working on the homework, working on the lectures. You should watch the lectures. There's stuff that's not in the book. PowerPoint slides, yeah, if you got to help too. It's going to take some work.